Okay, let's get started. So last week we studied the Zamochko theorem. So this week we use this Zamochko theorem or theorem to find the Landau-Ginzburg, so this model whose action is written here close to the minimum model, which is the CFD. So that's the goal of this first half of the lecture. Okay, so this is again this work is the Zamochko. '86. Okay, so suppose the so this is P equal to. So sigma is the capital sigma is the scalar field with this potential. Then so there's a G3. So here the degrees is increased by 1, but here degrees increased by 2. By 2 degree, exponent is increased by 2. So this is 1. Because at this point, sigma 2p minus 3 can be just removed. This term can be removed by shifting sigma with some constant appropriately. So I just said omit this one. Then this potential for generically has the p minus 1. P minus 1 local. Assuming the G is greater than 0. So this is G. Okay, so that's the potential we consider. And we just consider the quantum field theory with this action. And then if you consider the here, so all those are relevant deformation. So all those are the relevant deformation here. So the theory relevant scalar field. So relevant field is 2 times p minus 2 scalar relevant field. On the other hand, for corresponding. Okay. On the other hand, the minimum model unitary minimum model has the primary field. So 2 times p minus 2 primary field. Of the conformal dimension, h is less than 1. Okay. H is less than 1. Okay. So there's a correspondence between these and so this is a minimum model MP. I call it MP, which is MP p plus 1. So that's so if you consider R and S So let's consider the p equal to 5 case. Sorry, p equals 6 case. So, sorry, this is p equals 6. So this is p equals 6. Sorry, p equals 6. So that's 5. 5 local. P equals 6 case, as I mentioned many times, so there is an R and S. I don't remember which one is R and S. R and S. And then P equals 6 case, you have the vacuum 522, 533, 544, 555. Okay, so those are primary field. And of course, 566, so this part you omit. So the edge, so this is the 66 is here. But it hit the edge, so this is not included. And also here 521, 532, 543, 554. Like this. So those are the primary field with compound dimension less than 1. So this is most important. Do you know why this condition needs to be imposed? I'm asking you guys. Does anybody understand why? So when you compare with this scalar relevant field in Landau-Ginzburg model, so primary field, there are primary field in other places, there are primary field, but those primary field are compound dimension greater than 1, or greater than or equal to 1. Why do we need to consider H is less than 1 when you consider the correspondence? Does anybody understand? The important thing is this relevant. So relevant deformation. So when you have in 2 dimension, when you have action, and then to the deformation, whatever, G and then operator O. So relevant deformation. This operator O has to have the compound dimension less than 2 for relevant deformation. Okay, and compound dimension. So this dimension is 2 times H, because holomorphic and dihomorphic part. Okay, so therefore, so to corresponding relevant field, you need to impose this condition. Okay, H is less than 1. Okay. So, and correspondingly, those fields are corresponding to one-to-one correspondence between minimum model and another. And here HRS is, of course, as you might remember, I don't remember, sorry. Something like this one. I don't remember, sorry. Just a moment. So for okay, so like this. Okay, so that's the primary, RS primary. Sorry, no, it's not true. So this is just one. Just one. Sorry, this is the case. And then this is minus. Okay. So this is the conformal dimension of the corresponding primary field. So this is the formula for unitary one. And if you compute this one, you can see that this is less than 1. Okay. And also, moreover, so one can just compute the some OPE of this field. Okay. So OPE. So if you compute this OPE of this sigma, which corresponds to phi 2, it's supposed to correspond to phi 2. And then if you compare between phi 2, OP, phi 2, OP, this is 1 plus phi 3, plus phi 1, 3, phi 3, 1, this way. So, and if you look at so this 1 corresponding to this, I mean, like a 2-point function. The phi 3 corresponding to this the next sublating term of this OP, phi 3, which is exactly what happened here. Phi 3 corresponds to sigma square, and so on. And if you just do the computation of this cross phi r, what you get is the phi r minus 1. R minus 1 plus phi r plus 1, r plus 1, and then so on. Like this. Okay. And then those OPE will provide so like a sigma times z. Sigma r 0. Then what you have is approximately sigma r minus 1, 0. The appropriate power. I'm not going to write down. And sigma r plus 1, 0. The appropriate power and so those are the structure of OP between sigma field as an operator. If you consider OPE between these two, you have r minus 1, sigma to the r minus 1 appear in the leading order, sublinear order r plus 1, which corresponding to these conformal power. Okay, conformal power of the primary field in the middle. That's my evidence. Okay, so there's also a correspondence between operator in Landau-Ginzburg model and the relevant operator in Landau-Ginzburg model and the minimum model. That's it. And then, so the last step, if you look at the last step, so this last step, sigma 8 and 5. So this last step was exactly corresponding to p minus 1, p minus 2, corresponding to like this way. Like this way. Okay. And then if you apply one more, so 5, and then recall this, so in minimum model, if you consider P R X, this is P minus R and P plus 1 minus S. That's the symmetry the Mima model has because of this property. Okay. Because of this property, I hope I don't make a mistake. Yeah, I hope I don't make a mistake. I didn't make a mistake. Oh, it's okay. Yeah. So if you plug this one into here, it's satisfied. So the conformal dimension of both sides is equal to. From here you can just check. So therefore, so this one is in fact 5, 1, 3. It corresponding 5, 1, 3. Okay. And if you consider the OP of the 5 to 2, so one more sigma, application sigma, that will give you okay. So therefore, so this corresponding to sigma p 2p minus 3. Because I mean, if you multiply one more 5 to 2 corresponding sigma, if you multiply one more sigma, you get the 2p minus 3. Okay, 2p minus 3. But from the equation motion from here, this one is indeed equal to del bar sigma. That's the equation motion when GI, all the GI is equal to 0. So this is equation motion. Okay. And in fact, this sigma, so this corresponding to L minus 1 bar 5 to 2. Okay. So since sigma corresponding to 5 to 2 here, sigma corresponds to 5 to 2 here. But derivative of homomorphic and antihomomorphic correspond to L minus 1. Okay. And this is exactly what's included when you take OP between phi 1, 3 and phi 2, 2. So this square bracket means conformal family. So therefore, this one belongs to this conformal family of phi 2, 2. L minus 1, L minus 1 bar, phi 2, 2. So therefore, it's these relevant deformation and then primary field in minimal model, there is a correspondence between them. Furthermore, let's think about the normalization group by this relevant operator. Okay, suppose S is SP. So therefore, when GI equal to 0, when GI is equal to 0, so then this one corresponding to the theory with degenerate bucket. Like this, the potential become sigma and B sigma, and at the origin you have a degenerate bucket. So f of I of sigma equal to 0 is equal to 0, where I is the less than P. What was that? 2 P minus 1, like this one. Okay. Yeah, so that's the key. So degenerate bucket. So in the case of the So in the case, for instance, when p equal to 3, this is an Ising model. This is called Ising CFT. So in this case, vacuum, this is the sigma to the fourth. Sigma to the fourth theory. Okay, and then this one has the Z2 symmetry. Sigma goes to minus Z2 symmetry. And then p equal to 4, corresponding to tricritical Ising CFT. So that is the potential becomes something like this one, like this one. Okay. So this one has the Z3 symmetry. Z3 symmetry because of the sigma is just mapped to omega 3 sigma. It's also symmetry. It's also symmetry. Okay. Okay, let's consider the following deformation. Furthermore, you consider the following deformation. This one is the Landau-Ginzburg model, the LG model, LG theory, with the corresponding to minimum model MP. So the potential is something P like this one. Okay, and then you have the and then you deform the theory. And then let's see what's going to happen. So that if you deform the theory, so the theory will flow to other fixed point. So if you deform theory by 1, 3, deform theory, this is energy scale. This is parameter scale, and then so it is supposed to flow to the other CFT, from minimum model. And let's try to identify what's the corresponding CFT it is by turning on the deformation. So the deform theory. So this is almost marginal. When P is very big. And if you compute the coordination, 1, 3 is so this is equal to 2 minus 6 like this. So when P is very big, so it's close to the conformal dimension, close to 2. So it's almost marginal deformation. This is almost marginal. Okay. So that's the deformation we consider. Okay. And this, and here, this G, coupling constant G, will undergo the renormalization group flow, and dG and d lambda is scale. This is a scale. So this is the beta function for G. And then this beta function can be computed by just perturbation theory. So essentially what you need to do is that so you start with the action. And then g times d squared x dy, and then y13. You start with this one and do the perturbation theory. So really do the perturbation theory, which is something like so this is g, z, 1 minus g. Like this one, and so on. So if you compute this kind of perturbation theory, one can just compute. So this is it's just not. So it's just a correction function like this one. One can compute this beta function. This is the exercise for homework 5. And this can be derived, that the beta function can be derived like this way. C1 over 2 g squared. Where C1 is in fact OPE coefficient of so this C1 is the OPE coefficient. This is OPE coefficient. Okay, so that's so this is derivation is exercise. So let's accept this beta function at this moment, and then let's to see what's going to happen to identify CFT. Okay, and the most important information we know about what are the most important information given to the CFT. Given a CFT, what is the most important information? Good, central charge. So if you have a CFT, so the first question is what is the TTLP, and then what is the central charge? Okay, and these minimal models have the central charge, say CP, which is 1 minus 6 P times P plus 1. Okay, so that's the central charge we will get. I hope I'm not mistaken. Yeah, so that's the central charge we have. Okay, and then we just know, so that we already learned from the logic of this C. So under the information, there is some function called C, which is essentially decreasing, where H is given by this trace field, trace part of the trace integer. Like this way. Like this way. So this function C, let's try to construct this function C. Okay. And then the last time what we learned is that this C is the gradient flow of with this beta function. The gradient flow, what we learned last time is that 2 over 3. Okay. So the last time what we learned is that the the gradient flow of this function c is given is in function this beta function. Okay. So then, if you use this relation between this beta function and the c, we can mention that c of g is equal to ct plus alpha, some constant, times epsilon over 2 g squared plus c1 over 6 gk plus order g0. Okay, like this. So this alpha is unknown constant. Okay. So if you compute like this. So this is the initial condition, but if you take the derivative of c of g, what you get is the epsilon g minus c1 over 2 over g squared. Okay, times alpha. So that's the okay, and alpha should be oh yeah. So important thing is that the reason why I put alpha is that here there is the Zamochkov metric. Zamochkov metric RC, RG, and G whatever. G so there's some Zamochkov metric involved. So so I didn't include Zamochkov metric. So because we don't know the Zamochkov metric, you need to include this some unknown constant alpha. Okay. Okay. So this unknown constant can be evaluated as follows. Okay. So this delta c is minus 3 over 4 epsilon d r squared like this. Okay. So if you use this relation between the derivative, so as I mentioned, dot means the okay. So wait. Dot means r squared, the other r squared. So this dot means okay. So therefore, so delta c can be obtained by just taking nothing. It's given by integral by h. H is given by actually given here. Integral h like this. So on the other hand, we know that this trace part of the stress energy tension can be obtained by just stator. Can be obtained by G times 513 in our case times minus. Okay. Oh, sorry, it's not G, beta. Sorry, it's a beta. So this beta, the last time what we saw is that this one is equal to sum over A, beta A, operator A. In this case, the operator is we consider 513. So this is equal to minus beta 513. Okay. And then we just look at the beta over there. So it's the leading order is essentially leading order is EG 513. And then plus all the G squared. And then this is equal to epsilon G squared, 0 to infinity, okay. And then 513 R 513 0. Okay, 513 0. And this is just 2-point function of the primary field. Okay, this is just 2-point function primary field. So I can just evaluate it. So because in CFD it's easy to evaluate the 2-point function. And if you evaluate this 2-point function, what you get is a form. And maybe I can write down here. That's what you get from. So we simply just, this is equal to 1 over R to the 2 times delta 1, 3. Okay? And plug that into here, you get this one. So if you integrate out, what you get is that the delta C is equal to 3 over 4 epsilon G squared. Okay? So that's what you get. And if you compare with the previously, what was it? Oh, did I erase? No. If you compare with this one, delta, so the leading order, so this means that the alpha is equal to minus 3 over 2. Okay? If you plug into here, the leading order of this one corresponding to this one. That's how you fix alpha is equal to minus 3 over 2. Now, well, let's look at the function. So if you belong to CFT, beta function needs to be 0. Okay. Beta function needs to be 0. So therefore, the beta function looks like this way. Like this. So it's quadratically just a curve. And then so G star, this G star is the beta function of G star, it should be equal to 0. This means that the G star is equal to 2E over C1. Okay? 2E over C1. Now let's plug in to this value, minus this one. 3 over 2 epsilon G star minus C1 over 2 G star squared, like this way. Okay? Sorry, square and cube. And plug that into here, this is equal to Cp minus 3 over 4 squared. Epsilon cube over C1 squared. And the C1, this C1, actually we need to accept this one, but it can be written as follows. this OP coefficient 513 times 513. So what I meant is that this OP coefficient is, so what I meant is this one. This is 1 over R to the 2 delta, so 2H13 plus 1 minus R 2H13. And here you have a C1 minus the, okay, minus H13, so, and a 513, like this one, okay? So that's what you want to do. Like this, okay? And this OP coefficient of C1 can be just obtained by Dolchenko-Fatiev in '84. So this one I'm not going to give you a derivation. It's roughly square root 3, 1 minus 3 epsilon over 4 plus all the epsilon to the 4th. And just plug up into here. Then this one will give you Cp. And epsilon is essentially 4 1. Okay. And this is equal to Cp minus 12 over Pq. So now plug this one into here. Plug this one into here. Here Cp is the 1 minus 6 over P plus 1. And then this one is the order 1 minus 6 P minus 1P. Up to this P to the 4th. So this means that this the flows, so the IRCFT is in fact M P minus 1. This indicates, because this central charge is the P minus 1 unitary CFT. Okay. So although this technique of this renormalization group flow and also this Zamochko theorem, this gradient flow and so on, one can just identify what is the central charge of the IRCFT, which exactly corresponding to this P minus 1 unitary minimum model. So this is a great result, in fact. Okay. Good. And then from the okay, so then last time we just considered the we consider so-called anomalous dimension. So quantum field theory, in quantum field theory, scaling dimension also receives some correction due to the loop correction. And here we already know that the loop correction, so by beta function, which I just erased now. But last time what we learned is operator O, which will give you anomalous dimension. It's something like a sum over P 2 times delta AB minus like this. And in this case, so gamma hat of 513 is 2 minus del beta del G. So this is the anomalous dimension of phi 1, 3. The operator phi 1, 3. I think it's misleading to write down operator corresponding to phi 1, 3. Okay. And if you use the beta function, so beta function is given by 2, so epsilon times g squared minus the c1 over 2 gq. And if you use this one, this is equal to and then g equal to g star. Okay. And the g star is given over there. And plug that into here. So del beta del g g star is given by plus epsilon. Okay. And this is equal to minus epsilon. Minus epsilon, which is coming from just direct computation. So let's do that. Our computation del beta del g is equal to 2 times epsilon g minus 3 over 2 c1 g squared. And plug this g star over there. And this is equal to 2 over c. Like this. And this is equal to minus epsilon. Something strange. Over C1? Is it the case? Okay, but C1, we know this is the case. Is my calculation okay? Okay, so we're going to G equal to G star. It should be okay, right? So, no, it's not. It's not true. This is. Yeah. So this is. So therefore, this is the. If you take derivative, so you get this one, and then C1. You should correct C1 and then times G star. And plug that into here, what you get is minus 1. It's okay. You should correct it in 5 minutes. And this is equal to minus epsilon. Then plug that into here, you get the 2 plus epsilon. So this is an anomalous dimension. In RCFT, the conformal dimension of 2 plus epsilon is exactly given by, so this corresponding to 2 times H31. Okay. Therefore, even if you deform phi 1, 3, the IRCFT language, this operator become phi 31. Phi 31. So in IRCFT, this operator becomes phi 31. It's transformed into the different operator into the IRCFT. Okay, so that's what's really happening. Okay. And this is actually kind of natural to expect because I mean When you start, so the 513 is the most close to 2, it means that so as I mentioned, so this 1, 522, 533, 544, 554, 5 4, 2, 1. Which one is 1, 2 or 2, 1? 2, 1. 2, 1. 5, 3, 2. So 5, 5. And then this corresponds to the closest to 2 compound dimension. It's closest to 1 actually. So this corresponding to 5, in fact p minus 1 and p minus 2. And this is equal to 513. So that's the we turn on deformation. Okay. And this operator corresponding to a dimension sigma 2 p minus 2. So recall that the minimum model MP corresponding to the potential sigma, which is G times the normal model of sigma 2 times p minus 1. Okay. And tunnel deformation means this plus G so you just turn on information like this. So if you turn on this operator, so we can just mention this becoming irrelevant. So the term becomes this term dominant, become dominant. This becomes dominant, and this becomes irrelevant. And at the end of the day, it's flow to M P minus 1, which corresponds to B sigma is G 2P minus 4. Like this. So this is exactly what happened. Okay, so the upshot is that there's a correspondence between Landau model and minimum model, and then you can see the even renormalization group flow from one minimum model to the other minimum model by using this Landau model. If you use the Landau model, one can just and the minimum model. So this correspondence, you can also study this RG flow. So it's a very, very beautiful result, and then it's one of the milestones of the interaction between renormalization group and also CFT. So this is a very beautiful result by Zamochko. So which I wanted to explain. Any question at this moment? Okay, if not, I mean, it's a bit early, but let's take a break, and then after the break, I will move on to the higher dimensional conformal filter. Yes. Highest. This so the action is something like this. So this is the Lagrange, right? And the equation motion is just take derivative with relation with respect to sigma. That will give you the particular parts. This is the equation motion. So from this is Lagrange. So Lagrange, the equation motion. This is the equation motion. And then if you take the I13 522. And the first term you get is something like this one. 522, sorry. And teaches that. You should get this one. I don't. But this OP should to obtain. Can be obtained by direct calibration. Okay. No, but the one I wrote is coming from equation motion. I think I have answered your question. So I think so. If you compute this phi1 and the phi2 as the if you compute three-point function of the minimum model, phi1 plus 3 of x1 or something, phi2 2 of x2, and the other operator is phi of 0, right? Phi of x0. So if you compute this one, then have a three-point function has something like the form like x whatever 0 1 x some power x 1 2 some power and x2 0 some power and so on. And then these are contained. So this will, if you consider this three-point function, so here this conformal family. So if you start with phi 1 3, so phi 1 3, there exists such a singular vector at some point at the conform. So therefore, if you have singular vector, you have some combination of L1. I don't know, some L minus lambda combination of sum of L minus lambda acts on this one is equal to 0. The same thing happened here. So if you start with phi 2 2, it has some singular vector in a conformal family. That's how we define this primary state. And then this will give you differential equation. And if you solve this one, so you will know what kind of phi it should be. If you solve, so this will give you OPE of phi 1 3 and phi 2 2. You see, phi 1 3 and phi 2 2 OPE. This differential equation.
This is a 3-point function.
Yes.
We only have two fields.
Yeah, I understand. But I mean, once you take the phi 1 2, phi 1 3, 1 3, and x phi 2 2 of 0 is something like operator times x to the some power and so on, right? And then this all should be contracted with phi to get the two-point function, right? And that compound dimension should be equal, right?
So
Yes.
give the differential.
Yeah, differential equation. If you solve that one, so if you solve this one, you will see the constraints on compound dimension here. And what kind of operator you should get. That's you get.
Okay.
Okay. Okay. So let's consider the high-dimensional compound physics. So I'm updating the node in the overleaf, new node, and I will start with the free scalar field in section 7. So okay, so I will start with section 7, free scalar field. Okay. So now, the most likely today's 11th, and I heard in total there are 15 lectures. So 5 more lectures. We'll focus on the higher dimensional compound physics. So that's the plan. So to study the higher dimensional, CFT. Okay. And then first we study free scalar theory. Okay. So free scalar, massless, of course massless, because we want to study CFT. So the action is given by so action is this one, and the equation motion is given by like this way. Okay. So this is the equation motion, and then what is the compound dimension of phi? Good. D minus t divided by 2. So this is the scalar dimension of the scalar field. And this T mu is given by just usual calculation. It's given by like this way. So this is the energy momentum tensor. If you just use standard method to determine the energy momentum tensor. Okay, then and then you can see that if you take the trace one, this will become something like this one: 2 minus d divided by 2 partial mu phi partial mu phi. Okay, it's not traceless. So this it's not traceless. But this doesn't necessarily mean that it's it's not CFT. In fact, this can be written as follows. So if you use the equation of motion, this can be written as the 2 minus d over 2 partial mu phi partial mu phi, like this way, and this is equal to 2 minus d over 4 phi squared. Okay. And if you can write this traceless part of the, if you write the trace part of the stress energy tensor into some total derivative, this means that the theory is CFT. This part is already explained in the previous part of the lecture note. For instance, if you look at the section 3.2 and so on of the new note. In fact, if you can write down everything in terms of total derivative, trace part in terms of total derivative, so means that this T mu is total derivative of like this way. This means that the scalar invariant. This means that the scalar invariant. This one I'm not going to derive, but this one you can see my new lecture note in section 3.1. Section 3.2. That's you can do. Moreover, you can just make it traceless by adding some appropriate operator. 2 minus d over times 4 d minus 1, and then partial mu minus a mu and down row. Okay, and it's Pascal. If you add this one, you can check that this T tail is equal to 0. And it's totally innocent to add this kind of the total derivative part of to the action. Adding this concept of this action to the energy momentum test. Okay. So therefore, this means that the free scalar theory is a conform. So that's very free scalar theory is the conform. Actually, it's trivial conform. It's a trivial conform theory. And then if you add, if you put the theory, so this is the action for flat Minkowski or Euclidean space. So with R d minus 1 or something like that, or RD. So the action is like this way. On the other hand, to put the theory on a curve background, so that if you put the theory on curve background, Okay. So the action is in fact is given by as follows. So because of the so the theory, if you put the curve background, so you have to add this curvature term. This is the most generic action one can construct free scale here in curve background. Okay, so if you look at this R has what is the dimension of R? So mass dimension of R is what? Yeah. So it's so essentially R is something like G rho sigma derivative of G. I mean, roughly it takes likely like this form, and you have two derivatives involved in the computation. So therefore it has to be the dimension 2. So therefore it can couple with phi square because of the phi square has a dimension d minus 2. So this is the most generic action one can consider in curve. And then so there's something called so because they put the theory in curve background, means that so later we consider like radial quantization. So radial quantization means that later we consider radial quantization, so that radial quantization is always can be obtained by RT times ST minus. Okay, that's the radial quantization. Rather, we consider then S has a curvature usually. I mean, in the case of 2 dimensions, very too special. So in 2 dimensions, this cylinder, you can use the cylinder for radial quantization, but cylinder is just identify a strip in the left left edge and right edge in the strip, and just identifying the cylinder. So therefore, there's no curvature in 2 dimensions. Okay? 2-dimensional R cross S1. S1 does not have a curvature. However, if you go to high dimension, so this S has a non-trivial metric, so you can have a close, at least the even most round sphere has induced, if you go to a metric induced from this standard embedding of the standard metric, it has a constant curvature. So therefore, one has to consider this kind of action. Let's consider the okay. And then, so this theory, there is something called one can consider Wahl symmetry. Okay. So Wahl symmetry and conformal symmetry is very misleading. Many literature make a mistake. Conformal symmetry. It's closely related. Related, but not the same. So many people, many students get confused by the difference between Wahl symmetry and conformal symmetry. So last symmetry is the fixed manifold, Riemannian manifold, M and G. So this M is a manifold and G is a metric, and you just count the Riemannian metric like this way. So this is the Y transformation. So the Y transformation. So this is the Y transformation. So you just change the metric of the without touching any the manifolds. On the other hand, the Conformal transformation is a diffeomorphism. Conformal transformation diffeomorphism between these two manifolds, two Riemannian manifolds. So the Conformal transformation is you just consider two Riemannian manifolds, M1 and then M2, G2. So these two Riemannian manifolds, and you just consider diffeomorphism between these two Riemannian manifolds. And then G1, the pullback of metric of G2 under F should be proportional to original metric in G1. So using this, the diffeomorphism, one can just restore the information of G2, the target metric, so that restore the information G2 in M1. So that's how you can do. So this is a pullback. So you just pull back the information of the target manifold metric into the original metric. That is a pullback of the metric of G2. That one is in fact, if this pullback metric is proportional to the original metric, then this diffeomorphism is called a conformal transformation. So these two concepts are often is misleading, and then many students get confused, and then also anything. Some literature also make a mistake. But conformal transformation, Y transformation, totally different. But for instance, if you change the metric like this way, with this some omega is some function. It's a function on manifold M. Okay? Or omega function M. So therefore, if you do the Y transformation, curvature and so on, or everything will change. Curvature will change. On the other hand, if you use the pullback metric, the curvature at this point, for instance, let's see. So, anyway, so I think so there is a difference of F and point P and point Q. Q is marked P by the difference of F. The curvature here, computed with G2, should be the same as curvature here, computed by pullback metric F star G2. Okay. Curvature here is same information. So it's a different thing. So, but so there is some Zumino theorem mention that if the theory, physical theory, is while invariant, and then the diffeomorphism invariant, then this means that the theory is is equal. And this is the Zimino theorem, which I also wrote. I forgot the section. So section 4. Section 4 is the for Zimino theorem. I don't know if time permits. I will talk about this Zimino theorem later. Okay. So later, but this time I'm not going to. Today I'm not going to talk about Zimino theorem. And if you so if the metric G mu is transformed as like this way, okay, and then for even constant to be the action to be invariant, if omega is constant, then to be action invariant while transformation, the phi should be transformed as like this way. Yes. Am I correct? I think I just got confused. Am I correct? And now, sorry, something strange. Yeah, I'm not correct. Yeah, so this should be transformed as follows. D minus 2 minus 2. So let's compute. So if this is the case, G mu nu is transformed omega minus 2G mu nu. Okay, G mu nu. And this action can be written as follows. Okay, like this one. Okay. And if this is a omega minus 2 case, oh yeah, I forgot to include. That's why I got confused. Sorry, lecture is not correct. So S is equal to minus ddx square G. So you need to include this one. Yeah. Square G for carbon. Sorry. So this one you need to include. So then square G is transform omega a d of G mu nu. Sorry. Like this. So therefore, so in total square G, like this way. So the opposite should transform like minus d minus 2. Okay, so therefore it should be transformed to 2 minus d over 2 or 5 if omega is constant. If omega is constant. Okay, so that's the transformation rule for Y transformation. On the other hand, if omega is not constant, this partial derivative is not constant, then this partial derivative of phi is transformed as follows: 2 minus d over 2 of partial mu phi. Okay, and then plus 2 minus d over 2 derivative of mu log omega, like this. Like this. So that's a transformation rule where omega is not constant. And then to cancel, and also this Ricci scalar also is the Ricci scalar is transformed omega minus 2, r minus 2, t minus 1, d mu log omega. So this is the actually if you look at the Walt book, you can just find this formula. I mean, if you are interested, you can derive it. Minus d minus 2, d minus 1. Like this. Like this. So that's the transformation rule of the. That's how they transform. And so therefore, in order for this action to be invariant, so the C has to be particular body. So in order for this for S to be well invariant, C should be like this. Okay, so that's the how the so in order for the VAR, so the action to be the VAR invariant C needs to be quantized like this. So this is can be obtained by direct computation of this between these two. And moreover, if you okay, and then here, so this one is the diffeomorphism invariant. Diffeomorphism invariant. Invariant. So therefore, if this C value, then the theory is CFT because of this Zermino theorem. So although calculation is tedious, but if you set the C to be this value and plug this transformation into here, one can check that the action is invariant under the Y transformation. And then since this action is diffeomorphism invariant, therefore one can just see that the only particular value of C, this theory becomes the conformal invariant. So this will become important later. And then let's quantize. So quantize the quantization of the free scalar field. Quantization of the free scalar field. in Minkowski's. So R for 1 over T minus 1. And this way, I think if you take the QFT course, you already know what to do. You just do the Fourier transformation, and then square root to k, and then this one becomes, so the quotient in the Fourier transformation, Fourier mode, become 1 over here. Like this way. And then you impose canonical quantization condition. And then as usual, one has to do that. So total time canonical quantization. So then this item delta x minus 1. Then this generation is given by 2 pi t minus 1 delta k plus. So that's change. So this is the space coordinate quantization, and this is momentum quantization, and so on. So it's they are just related by Fourier transformation and vice versa. Okay, so that's what you learned. So let's compare ordinary QFT and then CFT. What's the difference? What's the difference between these? Okay. So first of all, for QFT, so in QFT, scattering matrix, naturally collected can be is described by momentum. Okay. Momentum space, and then perturbation theory and renormalization is perturbation theory. And the renormalization RG. Are all established in momentum space. And the correlation function is also in momentum space. Correlation function also in momentum space. So for instance, if you look at 2-point function always written like this way, p squared and n squared. Okay. For scale field, like this way. 2-point functions like this. So everything in momentum space, and if you go to coordinate space, you have to use its Fourier transformation, and then if you do the integrate out, you get some special function, Bessel function, and so on, which is much more different. In the case of CFT, the things are different. So in CFT, scattering matrix is not computed. No scattering matrix. Okay, so that's the thing. And also renormalization correction function from the say okay. So the okay. So I mean in CFT there is no renormalization. If you consider no renormalization. And then and also correlation function can be correlation function are described by even coordinate. It's not momentum. Okay. So there is some clear distinction between the what you can do in CFD and what you cannot do in CFD and so on. So let's look at the why this is the case. So for instance, two-point function. So in the free theory, phi p2 is given by like this way: 2 pi to the d delta p1 plus p2 to 1 over p1 squared. Okay. So that's very standard for free theory. Free theory. So this is the case. And if you do the Fourier transformation of this one, what you get is as follows. Is given by C x1 d minus 2. So, and the C is in fact some function of the like this. And this is actually will give you the area of unit sphere in S d minus 1. So that's so therefore in free theory, so even if you write the how to say the momentum or coordinate space, not so much different. Because I mean, if you have this is m squared, things are different. If you integrate over, you won't get something so simple. You always have some decay function is involved. Definitely, it's because I mean correlation function is expression has to decay. It depends on dimension. You get the power is depends on dimension. But for free theory, one can just 1 over p squared. You can do the Fourier transformation very easily to get like this. And as you can easily see, so here, so we know the free scalar delta is the d minus 2 over 2. Okay? So therefore, this can be written c x1 2 and then 2 times delta, which is 2 times delta, which is just obtained from the conformal symmetry. Okay? Conformal symmetry. Okay. And then use the width theorem. Let's compute correlation function, lots of correlation functions. So width theorem, which we already learned many ways, but just taking the contraction between 2 and so on, and normal ordering, So one can compute many correlation functions in free series. So phi squared x1, phi squared of x2. And this one, normal ordering. So this one can be just obtained by just the phi x1, phi x2, and then phi x1, phi x2, and times 2. So there are two ways to do the construction. Essentially, what you have is phi x1, phi x1, phi x2, phi x2, and then weight contraction is this way, or like this, weight contraction. There are two ways to do the weight contraction, like this one. So therefore, this one is equal to 2 times c squared x1, 2 times d1. And then there is some mistake in lecture note. And then, of course, we cannot have this. So we cannot. So this weight contraction, phi x1, big x1. You cannot take this contraction because normal order x2. Okay. So here it's normal ordering is assumed. So if left, so the creation operator is to the left or annihilation operator to the right. So therefore, if you have a same point operator, this correction normal ordering will tell you that this is 0 at the same point because of same. Okay. So therefore, from this computation, one can treat this one. In free theory, this one is primary field. With a compound dimension d-2. Okay. So it's very simple computation, but if you try to go to this one into the momentum space, if you try to compute this correlation function in momentum space, it's going to be very, very, very complicated. So you have to do lots of calculation. But in CFT, you can just use the Wickstrom normal order to compute this one. The other thing, also, 3-point function one can compute. And this one is equal to 2c squared. Okay, let's start. Okay, so this obeys the same rule of the conformal symmetry we mentioned at the distance. Conformal symmetry will tell you this one is equal to x12 h1 plus h2 minus h3 x23 h2 like this, divided by structure its denominator. And now, so in our case, h1, h2 are sorry. Yeah, it's okay. So h1, so h1 is now h1 is d minus 2, h2 is equal to d minus 2 over 2, h3 is equal to d minus 2 over 2. So that's the case. Okay. So h1 is this one. So therefore the d minus 2. In fact, anyway, so maybe any h delta is here is the same. And then if you use this, if you plug this one into here, h12, h31 will take this one, but the h23 is the, if you sum them up and the minus this one is equal to 0. So therefore this does not contribute. Okay? Therefore it's okay. It's the what the conformal symmetry predicted. And we can do the same thing. I mean, straight scalar is just big contraction. Okay, so how to get the 8? So this is 2 to the 3. Okay. Okay, so essentially you have x1, x2, x3. And then, so this is x1, x2, x3, and then you just how you just put them together like this way, or something like this way, and so on. So that will give you 2 to the cube, 2 cube choice. And this one is equal to like this, and which is exactly the form of this orange one. So now what you need to put everything like this way, okay? Like this way. Fine. Five x2, 5x3. 4-point function one can consider. This one is also pretty easy. So you just have x1, x2, and with 0, x3, x4. And then how do you pair? Either this one, or this one, or this one, depending on like this way. And one can just obtain as follows. C squared x12 d minus 2 x34 d minus 2 1 over x13 d minus 2 1 over x34 d minus 2 x14 d minus 2 123 d minus 2. Okay. It's a boring, but it's you can obtain like this. So it depends on how you do the wing construction. The important thing is that we already knew that so you did the exercise, and then I didn't print out this part, so I need to. Wait. Okay. So 4-point function. So 4-point function in CFT is generally you have this kind of form. And then U and B are cross relation, but the same thing happened here. So this one can be written C squared divided by x12 d minus 2 x34 d minus 2 1 plus u d minus 2 over 2 plus u d minus 2 over 2 d minus 2 over 2. Okay, so that's the what you obtain from. And U and B are cross ratio, so I think we already knew, but I think I should. U is equal to B is equal to so these are cross ratio. And since we now delta 1 and delta 2 configuration are same, so therefore this is back out become 1. And this configuration is same, this become 1. But slab is this one is equal to this one, and then GUB is given by this. GUB. So therefore, this is as predicted from conformal symmetry. Okay. So, but those are the just using Wick's theorem and normal ordering to compute all the correlation function for free theory without performing the momentum integral. So that's one thing. Like one nice thing in CFT. Usually you cannot do that in the online QFT. You have to do the loop integral to do the computation and so on. But now we can just do everything in terms of coordinate space with the Wick's theorem normal model. Especially this can be done because it's free theory. Any question at this moment? Okay, so now I will talk about the quantization of the cylindrical space. Okay. Cylindrical space. So now we will do that quantization. Or maybe radial quantization. Or is d minus 1, especially when d equals to 2, d equals 3 is the most simplest example, but this captures essential feature. Again, the action is given by this. So the d equals, I will explain why d equals 3 is simplest, because I mean d equals 2 we already learned by cylindrical radial quantization. After d, you have to do, so as you will see, so you have to do the spherical harmonics decomposition of the spectrum. So here, the first space, you just can do the Fourier transformation very easily. But for S, for sphere, because of curvature, you have to find a nice orthogonal function, so which is spherical harmonics. And the d equals 3, you already learned in quantum mechanics. So d equals 3 is the simplest. And so that's why it's essentially capturing essential information. Like this. Like this. And then, so now, so in the case of so in the case of the first space, Minkowski space, the Fourier model is like this way, and the K is continuous. But now it's like a compact space. S is a compact space. So therefore, momentum space is discretized. It's no longer continuous. And then we can just do the following. So if you do the decomposition of the Fourier model, everything becomes discretized. Like this. Okay. So and here, YLM is the spherical harmonics. And so. So that's the eigenfunction. So therefore, so the Laplacian of S2 acts on YLN is the ELN and then YLN. Okay, so those are the, so Laplacian of S2 is the, I think you guys can write, right? I already forgot how to write. It's something like, I don't remember, phi squared plus, how do you write? E? It's not, is it phi? I don't remember. Like a sine squared like this way? I don't remember. I don't remember. Sorry. Anyway, Laplacian of the S2, I think I should teach quantum mechanics. Otherwise, I don't. Anyway, so this is spherical harmonics that appear in quantum mechanics. L is the angular momentum in the, and M is the z direction of the angular momentum. And then sorry, I told you wrong. So this is not ELM. This is just a just L times L plus 1. So it's just this. But now we have a curvature term, so CR. And if you consider just unit here, just R is equal to 1. So therefore, E squared is the L so So now, as I mentioned, when C is some constant, the discrete value for D minus 1, where D equal to 3, this is equal to 1 over 8, right? Only this value of C, it becomes conformal. So if you plug this one, it's something very natural, miraculous thing happen. So 1 over 4, which is the okay, so therefore ELM is just L plus 1 half. Okay, so that's the so therefore E can be written like a linear in L. When you have this particular body of C. So the feature very nice. And then, so if you do that canonical quantization, so what you get is that the and the vacuum is this kind of like this for any. So this A treat as an Eilish operator, and this one will create acts on vacuum to get a non-trivial state. Okay. Okay, so then, so the state operator correspondence of this this radio quantization okay. State operator correspondence is the, for instance, the phi limit of t goes to plus I epsilon and the phi of time. So that is corresponding to that is corresponding to the A00 cover e to the I E00 and also. So therefore, Okay. So this means, I mean, plus epsilon? Yeah. Yeah, I think, sorry, I think the correct prescription is something like 1 minus I epsilon infinity minus like this. Yeah, correct prescription like this way. This this I epsilon prescription means that you only pick lowest mode of the energy. So that's if you take t goes to minus infinity. So lowest mode is 0, 0. Sorry, so it's creation operator 0, 0. So 0, 0. So you only pick this one. So therefore, state operator corresponds 0 corresponding to a 0, 0 down over. That's the state operator corresponding. And then, if you consider you can also consider ALN, like from omega. Okay. All those states you can consider, and this has the energy eigenstate. Okay. So this will create energy eigenstate L plus 1/2, and this has the spin L representation of the SO3 that rotates S2. So we just consider space-time is the S2. So now we consider R cross S2, and then so you just do the spherical harmonic on S2 that corresponding to state operator correspondence. So you just have to like this. Okay. So yeah. So this is symmetric. And traceless. Traceless means that since you have a equation motion, this is equal to 0. So therefore, any contraction with indices of mu1 to mu_l, if you take a contraction due to this equation motion, it becomes 0. Okay. So symmetric. So this will give you the conformation of the delta. So this is corresponding. So this delta is equal to L plus 1/2. So as you know, so in 3 dimension, action is given by here. In 3 dimension, this is the phi has a conformation 1/2, right? 1/2. And it's natural to, so this is a conformation of 1/2, and since 0, 0, so therefore spin 0 means the energy is also 1/2, okay? Because L equals 0, so therefore conformation energy agree. The same thing happened for here. So conformation, because of the derivative action here, becomes L plus 2 or plus 1/2, and this one also has an L plus 1/2. Therefore, the 1-to-1 correspond. And then, yeah, it's a spin L representation of SO3. Okay. So again, so to do this correspondence work, so to set this value is very important. To set this value is very important. Otherwise, you don't get this 1/2 shift. Okay. Okay. And then this part, I think I need to take a look at the latest report. I printed out the old version, so today I need to take a look. And also, you can consider multi-particle. So this is single particle. These are single particle. Single particle is only one A axon. So this is single particle. So how about multi-particle? So for instance, one can consider So A00 dagger, A00 dagger, axon backing. So what is the corresponding state? Corresponding operator? So before. Huh? You can guess her. So that's the corresponding operator. So of course this is the L equal to 0, conformal dimension equal to 1. Okay. Okay. And for instance, if you consider L equal to 2, delta equal to 3, one can consider following state. Like this one. Okay. And this corresponding to this is L equal to 2 means that there's something like this one. So you have this two direct axon the phi square, actually phi square, and that will give you L2. Okay, and then the other. So L equal 2 and then delta equals 3 is also accurate. Okay, like this one. And then and also we need to consider T mu. This is also symmetric, traceless, and then L equal to spin 2 operator. Spin 2 operator, and this one is also so if you recall, T mu is something like a down mu phi, and then so minus A mu over 2 down mu phi, and then in addition to that you have something like a plus 1/8 down mu and then phi squared. So this kind of term will appear. Okay. And then, of course, because of this one, so you get that you need a two action of this A1 there. So therefore, so this operator and T mu correspond to linear combination of these two states, and so on. So this is a multi-particle version of this. And then, yeah. So it's very difficult to find, yeah, so if you go to the math particle, say it's very difficult to find the state operator correspondence in the usual high dimensional theory. It's very difficult if you go to the, anyway, so that's the S d equal to 2 case, d equal to 3 case, and then you can do the similar analysis for alter D using Sprague harmonics, but I'm not going to go into it. So these are just the simplest example for Sprague harmonics. Okay, so those are the free scalar theory I want to introduce today. Any questions at this moment? Okay. So now, to move on from free theory to arbitrary, like an interacting CFT. This is free CFT, which is very easy, but the interacting CFT is much more difficult. So to study the, I don't think, so only 10 minutes left, so I don't think I can go into detail. So to study the interact CFT in high dimension, what we need to do is what? What we need to do, can you guess? So we need to study representation of conformal. We need to study. So it's like the same as Virasoro algebra. So you start with the Borel module, but if you look at some particular Katz determinant become 0, you will see the singular vector, and after that you create a lot of null vector, and to get the irreducible representation, you have to throw away and so on. That's what we learn from the two-dimensional CFT. So we should do the same thing. We should do the same analysis in the same analysis as in 2D, but 2D is infinite dimensional, but high dimensional conformal algebra is not infinite dimensional. So the analysis is big. But anyway, so let's start with the primary state. Primary state. So which is defined as K mu or I is equal to Z. Okay. And then so just recall what's the primary state. Or I is given minus I delta and K mu. Like this. So this is confirmation. So this is representation of SO where 1 comma d minus 1 or SOD or SOD. If it is Euclidean, Okay. So you can get the formal module. So from formal module, it just acts on the derivative. Like this. So those are formal module. So primary state and those are descendants. And this is primary. And then so you can just act on a number of times p mu 1 total p mu l acting on operator. The primary state like this one. And then those are the bound modules. So these are bound. And the question is, are there singular vector? Okay. Are there new state? So one can ask this kind of question. And then of course the math exists. So for instance, we can just take a look at the. So we know some linear combination of this one will give you T mu corresponding to T mu stress energy tensor in free theory. But we know that the stress energy tensor will obey this kind of equation motion. Okay? Equation motion. So therefore, so there is some state corresponding to T mu nu, acts on P mu. It should be equal to Z. Okay. This should correspond to at least should be nu vector. So the expectation this should be nu vector. Or more representation theories. So nu vector or singular vector. Singular vector. So recall the difference between nu and singular. I didn't explain last time, but I also let's recall. So singular means subhead, and then in bound module, one module and descendant, and then that is another by K. And this is necessary to be the null. This is singular. So null vector is the null. Is here. Then I is null. Okay. Actually, since null is very big. The singular is very small, tiny piece. Those are singular. So singular vector is included. Of course, if you have a singular vector, one can easily show that this is equal to Z. This is equal to Z. Okay. And then, so I don't think I have a time, but next time I will explain how to construct the singular vector in the this Bauman module, and then a little bit talk about the unitary development. So that's the plan of the next lecture. Are there any questions? Okay. So let me. Few minutes are left. Can I ask you some questions? So, what did you learn today? What? From today's context. So every Sunday, I always attend the Chinese lesson. In the last 5 minutes, my teacher always asks, the content I learned, or content, no, or some new vocabulary to you. The lesson learned, I have to. So what did you learn today? What did you learn? Can you, what's in your mind from this context, from today's lecture? Good, good. So the first one is what we learned is the so LG minimum model correspondence. Okay, what else did we learn? What? Okay, especially high-dimensional free high-dimensional free high-dimensional scale theory. Okay, what else did we learn? Archie flow, good. So here it's contained here. So Archie flow from MP to MP minus 1. Okay. Yeah. Triggered by 513. Okay. What else did we learn? What? Good. So radial quantization on S1 cross R cross S2, especially S2, and the state of operator correspondence. Okay, those are more or less chapter. Okay, so those are what we learned. Here, especially free theory, we compute correlation function. Correlation functions of the times up. If it is consistent with analysis of the conformal and so on. Okay, and then especially this LG minimum model correspondence is very beautiful example where you can learn renormalization groups or variable. So, and somehow one side is just Lagrangian description, have a Lagrangian description. Then the other side is only coming from the representation theory of universal algebra. Somehow they just agree by our shift. So that's a very beautiful correspondence. Okay, let's stop here.